Okay, give me 1 second. I don't know what's going on here. Okay, so integrating with respect to z, that's the first variable we integrate with respect to. So that's, well, we have the integral from 0 to 2 pi, the integral from 0 to 3, and the integral of r with respect to z, that's going to give us r, z evaluated from 0 to 9 minus r squared, dr d theta. Well, recall in this case, so we obtain a two-variable expression, a two-variable function in our integrand. So we have to, these limits, 9 minus r squared and 0, should be evaluated only in z, not in every single variable. So that means, so that's the integral from 0 to 2 pi, the integral from 0 to 3, r times 9 minus r squared minus 0, but well, minus 0 is simply just 9 minus r squared, dr d theta. Alright, so let's keep integrating. Now we're going to integrate with respect to r. Everything right here is in terms of r. However, let's distribute to make our integration a lot easier. Integral from 0 to 2 pi, integral from 0 to 3, so that's 9r minus r cubed dr d theta. So that's the integral from 0 to 2 pi, integral from 0 to 3, and the integral of 9r, that's no more integral actually, that's just 9r squared over 2 minus r to the 4 over 4, evaluated from 0 to 3. And don't forget the d theta. Well, as usual, upper limit minus lower limit. That's the integral from 0 to 2 pi. So that's number 1, 9 halves times 3 squared minus 3 to the 4th over 4. So that's our first evaluation. Minus, how about big 0? Because if we evaluate this 0 in r, everything is going to get zeroed out. And that d theta. So, okay, let's simplify. So that's 3 squared, which is 9 times 9. That's 81 over 4. Is that what I got? So 81 over 4. It looks like I got a different result in my... Oh, okay, no, that's fine. And minus 3 to the 4th power over 4. So that's 81. Well, that's 81. 81 over 2 minus 81 over 4. Right? Mm-hmm. D theta. And this equals to 81 over 4. D theta. Which we can take out of the integral. And that's the integral from 0 to 2 pi of d theta. So that's 81 over 4 theta from 0 to 2 pi. And that's 81 over 4 2 pi minus 0, which is simply 2 pi. And we can divide out the 2 with the 4 right here to get 81 over 2 pi, or 81 pi actually. That looks better. Alright, so 81 pi over 2. It's the, what's in this case, the volume, right? Oh yes, it's the volume, so we're asked for the volume. Okay, so let's look at another example on setting up or evaluating an integral. Oh, okay, but first of all, by converting to cylindrical coordinates. Yes, no, you don't want to do this using rectangular coordinates. I mean, even if you evaluate this integral like this, okay, let me try it real quick. Radical for short. Okay, the integral of x squared and y squared with respect z, that's x squared, z plus, or simply x squared plus y squared z dy dx evaluated from this radical to 2. But well, when you do upper limit minus lower limit, so check what we're going to get. One of the limits, well, actually, I'm just going to write the function x squared plus y squared times 2 minus the square root of x squared plus y squared. So when we want to, when we try and evaluate the integral of this madness right here with respect y, for example, it's not going to work because that's x squared plus y squared. If we said u equals x squared plus y squared, du with respect to y in this case would be 2u, but we have a y squared outside plus some x squared, so that's not going to work for our u substitution, all right? So that's why we have these cylindrical coordinates to simplify our lives in this case for triple integral. So all right, so whenever we have these limits right here, so we should interpret them the following way. Number one, this dc right here is related to this innermost integral. Okay. So what is this telling us in the, well, that's going to tell us something. We're going to look at this later actually. Let's look at second integral. That's the second inner integral. That is the one with respect to y. And I think this one is, it's a lot easier to see. That means this is telling us that y is varying between negative the square root of 4 minus x squared, whoops, and 4 positive root of 4 minus x squared. All right, and this outermost integral is telling us that x varies between negative 2 and 2. So we can use these pieces of information to find out what's going on in the 2D plane. So that's x going between negative 2 and 2. And well, so what is that going to mean? So if I set just one of the sides right here, so I'm going to take all this, y equals to the square root of 4 minus x squared. If I square both sides, that's going to be y squared equals to 4 minus x squared, and x squared plus y squared equals to 4. What's this? It's a circle, right? It's a circle of radius 2, right? And that actually agrees with the limits with respect to x, right? To go between negative 2 and 2. All right, so that's negative 2 and 2. All right, those are our limits with respect to x. And well, the fact in this case that we have the upper semicircle and the lower semicircle, that means that the angle is going to vary between 0 and 2 pi. That is, we're going to go around the circle in this case. So from here we can start setting up the limits with respect to the new variables. However, I would like to start with the variable z in this case. So in this case, z equals to well, actually, z is varying between 2 and, well, actually, no, the reverse order. The square root of x squared plus y squared and 2. But we need to try to rewrite this using our new coordinate system, which in this case is r and theta, right? R, theta, and z. Well, recall that r squared equals x squared plus y squared. That's one of our formulas to convert between polar and Cartesian. If we solve for r, that's the square root of x squared plus y squared. And well, we can replace this with z varying between r and the constant 2. All right, the constant just remains the same. So we have the innermost limits of integration for the new transformation of coordinates. All right, what about the next variable y, which in this case it's going to be for r. All right, so r varies in this case between, how about 0 and 2. All right, between 0 and 2, and the angle theta, because in this case we're going around the entire circle, that's going to vary between 0 and 2 pi. All right, and so you might ask yourself, why is r not varying between -2 and 2, even though we're saying this limits? Yes, but the thing here is varying between 0 and 2 for the right side of the circle, but because we're going around the whole circle, though, that's going to be, again, you can think of it like an absolute value, if you will. So that's going to be 0 and r. And so I think we have pretty much everything ready to set up our integral. All right, so what about the integrand? We need to rewrite this x squared plus y squared using terms of cylindrical coordinates. What is x squared plus y squared equal to? R squared. So we may go about writing the integral. So we're going to have the triple integral of r squared. Now, another thing. What is dz, dy, dx going to become in cylindrical coordinates? R, dr, d theta, but we're missing something. dz, right? dz, z remains the same. So, all right, r squared, r, dr, d theta, dz. And well, that's the integral from, what are we going to have? From r to 2, and then from 0 to 2 for the radius, for the radius, yes. Oh, wait a minute. It's dz, dz, dr, d theta, 0 to 2 and 0 to pi. 2 pi. Yeah, I had the wrong order in the differentials here. So let's evaluate this integral. So yes, the setup of the integral took a little while, but in the end, look at the integral that we're going to evaluate. Instead of trying to evaluate another, another integral that otherwise we can't evaluate, I mean, this is a lot simpler to do. So, number one, this becomes integral from 0 to 2 pi, integral from 0 to 2, from r to 2, that's r cubed, dz, dr, d theta. All right, and well, first of all, we integrate with respect to z. That means r cubed is constant, so that's going to leave us with the integral from 0 to 2 pi, integral from 0 to 2, and that's r cubed z, and that gets evaluated between r and 2. Don't forget our dr d theta. And again, let's highlight where are we going to plug this in. So we plug this in our z, all right? That's where we do our fundamental theorem of calculus. Again, I will keep doing all this highlighting. Where do we back substitute when we evaluate via the fundamental theorem of calculus? Because this is a very common mistake to plug in every single letter that you see. But again, notice we evaluate an integral with respect to z, so we should evaluate at the z's. All right? Okay. So that's the integral from 0 to 2 pi, the integral from 0 to 2, r cubed, z, which is 2 minus r, dr, d theta. And while distributing this, it's going to give us the double integral from 0 to 2 pi and from 0 to 2 of 2r cubed minus r to the 4th dr d theta. Okay, so the integral, we may now go about integrating with respect r. So that's the integral from 0 to 2 pi. No more the second integral symbol because we're integrating. So that's going to be 2r to the 4th over 4 minus r to the 5th over 5. And that gets evaluated between 0 and 2. So we're lucky that one of our limits is 0. That way we don't have to perform a really big arithmetic operation, right? And don't forget the d theta. So as usual, upper limit minus lower limit. So that's the integral from 0 to 2 pi. And well, that's 2/4, which reduces to 1/2. How about that? So that's a 1/2, and that's 2 to the 4th power minus 2 to the 5th over 5 minus, well, evaluate all this at 0. No need to show the calculation. A big 0 is fine, all right? To save time when showing this work. All right, so that's going to be 2 to the 4th, which is 16 over 2. That's an 8. Eight minus 32 fifths. And d theta, so what's 8 minus 32 fifths? So that's 8 times 5, that's 40. Minus 32, is that 8 fifths? Yep. And those 8 fifths, I'm going to write them outside of the integral. So we can integrate this easily. So that's 8 over 5 theta from 0 to 2 pi, which is 8 over 5. 2 pi minus 0, and well, that's 16. Whoops. 16 pi over 5. Sounds good? All right. What's next? Oh, spherical coordinates. All right, so that's one method, that's one new system of coordinates, the cylindrical coordinates. And again, this cylindrical coordinate system, it's nothing other than the polar system in 3D. I mean, the 3D part, it's just the z remains the same. It's a circle, a stretched circle to turn it into, I mean, a cylinder. So that's why it's called a cylindrical coordinate system. All right. The next system, triple integrals in spherical coordinates. Well, so this one is going to have a few more elements than just r and theta, because in this case, well, we're not going to look at points in a cylinder. We're going to look at points in a sphere. We're going to look at different radii and also different angles that comprise this system here. So let's see. Number one, it's another triple of the form phi, rho, and theta. All right. And well, other authors, other books list the order triple in different order. Actually, I didn't know it was kind of sort of controversial when I was looking on the internet that physicists use it one way. In one order, mathematicians use it in a different way, and actually I think, let me double check real quick. I believe I have a typo. Yes, I have a typo. This one is supposed to be rho, phi, and theta. So I have the phi and the rho reversed. All right, that's a little typo there. Alright, so let's describe each element of this new order triples. This rho, which is actually the symbol that we're going to use for the radius of the sphere, and it's also the same symbol that you use in chemistry for the density. Alright? Well, that's the distance between the origin and that point, which in this case, let me highlight. So that's me highlight in red. And let me highlight that distance r. All right. Well, phi is the angle between the positive z-axis and the like segment OP, which in this case, well, that PR. Well, actually, I have an animation for this because if I try to explain how it works, it's going to be just weird. So the visual will for sure be a lot better. And well, what about theta? Theta is going to be exactly the same angle as in cylindrical or polar, because in this case, again, we have a solid. We need to understand what's going on in the xy plane, that is in the floor, in the floor of the solid. And it turns out that this is the angle formed from the positive axis and the point and the projection of the point. Well, actually, to be more accurate, it's, well, the point is right here. This is the shadow of the point, so it's this angle right here, theta, which is the projection into dimensions. All right, usually the trickiest angle to see when it comes to spherical coordinates is the angle phi, which is actually the angle, okay, let me lower this a little bit. So it's the angle formed from the positive z-axis, and it does all this. Its range goes from, for example, if this is, say, 30 degrees, when we get to the y-axis is 90 degrees, we keep sweeping this until we get to the negative z-axis, and then we have reached 180 degrees. All right, so let me do this by hand real quick, and then I'll show you the animation. So for example, this is for example 30 degrees. All right here. Then by the time we get to the positive y-axis, that's the angle between the z-axis and the y-axis, that's 90 degrees. And if we keep sweeping over here, maybe 90 plus 30 degrees, 120 degrees, and 180 degrees. All right. Okay. Let me pause the recording for a second. These are the convert. Yes.
Did you miss a box to fill in on the last page?
Which one? Oh yes. This means theta goes between 0 and 2 pi. Yes. So which is what we have over here, pretty much. That piece of information, right? All right. Yes. These formulas are a little crazy to try and memorize them. So don't memorize it. And again, on exams, you're allowed to use sheet of notes. So this is what you want to have on your sheet of notes. Okay. Actually, we're going to derive all these formulas, and we are also going to derive the volume element for the transformation of the integral as well. Just to briefly review, how do we go from a point in x, y in the rectangular system to r theta, to polar coordinates? So the idea right here was that actually this point forms a right triangle here, x and y, and we have the angle. So x equals okay, this has a length r cosine theta, and y equals r sine theta. So the formulas to convert between the polar and rectangular came from basic SOHCAHTOA, right? That's all it is. Now, when it comes to spherical to rectangular, so actually there's another handout. Did all of you get that one? Again, I like this picture better because, I mean, this gives us a better perspective of what's going on. You know, this point is the origin to whatever the point on the sphere. And then we have a picture of what theta means, which is just the angle in the xy plane. And we have a picture of what phi means, which is the angle between the positive z-axis and the negative z-axis. All right? So we're going to use the picture right next to it to derive these formulas for conversion. So number one, we're going to consider the vertical component and the horizontal component. So number one, let's label. First of all, let's label. So this is the point right here. That's to get to this point, we need to move x units in the x direction, y units in the y directions, and up z units to get to that point P, all right? Well, so one thing to observe here, the trick, if you will. So let me focus on this rectangular shape. I mean, even though it doesn't look rectangular because of the perspective, trust me, this one right here is a rectangle. And what am I going to do? I'm going to do this. All right? I'm going to do this over here. So this is the z-axis. This is the point which has a row over here, and this angle which is this phi. Okay? However, by symmetry, isn't it that this angle right here, it's the same as that angle as well? Alright? Okay, so I'm going to take that part of the triangle right here. I'm going to take this triangle right here. I'm going to call this phi, this angle phi. And well, this side right here is going to be z, this is rho, and this is, what was that? Supposed to be, oh, this is r. Let's call it little r. So we're going to call it little r because, again, this line right here, this segment, it's actually on the xy plane, creating that circular base, if we will, all right? And well, if we look at the projection in 2 dimensions of this, this is essentially what we're seeing. X and y, so this should be the radius r. Again, just to make a distinction, that little r is just the radius of the circle generated by the shadow of the sphere. But the rho right here is the radius of the sphere. 2 totally different radii. All right, 2 totally different radii. All right. So from here we can get a couple of relations using SOHCAHTOA. So cosine, or rather sine phi equals. Okay, careful with the orientation of the triangle right here. Sine, which is opposite. The little r is opposite over hypotenuse, which is rho, which means r equals rho sine phi. And we're going to use this one a lot, the rho sine phi. And at the same time, we can get cosine phi, which is adjacent, that is z, over hypotenuse, which is rho, which means that z equals rho cosine phi. All right? Again, basic trigonometry, basic SOHCAHTOA. So that's one setup. So that's one relation of formulas right here. We're going to, and that relation, we got it from, let me color this one right here. This, we got it from this triangle. Now we're going to set another triangle. So that's the triangle in the solid direction, in the z direction. So we are going to set up another triangle in the plane direction, in the xy direction. All right. So this is going to be given by this. All right. So I'm going to draw another triangle. Let me draw it here.
You want me all the way down?
All the way down. Oh yeah, that's true. Yes, thank you. Yeah, perspective, right? Yes, this one right here. Thank you. All right, so this one is going to be in perspective in 2D. It's going to look like this. This one right here. For which in this case the angle is theta, and the components are x and y, and this is r. I mean, it's this one is going to be exactly the same as the cylindrical and polar. Well, so from here we get that x equals to r cosine theta and y equals r sine theta. Well, so actually we already got the z. If you notice, z equals rho cosine theta. Check on the other hand that isn't it the same? Let me go back actually so we can all see it together. This one, isn't it the same? We already got that one. Let's get the other two. Well, so notice the conversion formulas in cylindrical coordinates do not involve little r. So for x and y, we need to get rid of these r's. Alright? How do we get rid of those r's? Well, it turns out that we have expressions for them. Because, well, what's r? Isn't it phi, sine, no, rho sine phi? Plug it in here, plug it in there, and we got it. That's rho sine phi, rho sine phi, cosine theta, sine theta. And those are the three formulas to convert. Alright? Those are the conversion formulas from spherical to Cartesian. And yes, even though the picture looks a little complicated, but in the end, everything comes from SOHCAHTOA using just two right triangles. That's all it is. All right. So let's apply this to convert. Well, I'm not gonna have the book. Let's apply this to convert some points. Okay, let me know when you guys are ready to go back to the other handout. All ready? Mm-hmm. All right. So, okay, so working? Okay, perfect. All right. So convert between cylindrical to spherical. All right. So the formulas to convert from cylindrical to spherical. Well, in this case, we're going to use the spherical ones to cylindrical, which in this case are, well, those are not the ones that we derive. We derive the other ones. So we're going to use these ones right here. All right. Number one, let's label this point, this order triple. Let's label it as this is r, this is theta, and this is z, because this is cylindrical coordinates. Cylindrical coordinates are of the form r theta, just the same way as polar coordinates, but in this case we have that third component z, which is the same, it's just z. All right. So on the one hand, well, how do we go from r to rho? Okay, so in this case, from one of the relations that we have here, this one in particular, so we know that
How do you know it's r theta z and not the rho phi theta?
Oh, that's because we go from cylindrical, this is cylindrical coordinates, to spherical coordinates. So the end result will be of the form rho phi and theta. All right. So let's check this out. So number one. So we know that rho equals x squared plus, or rho squared, x squared plus y squared plus z squared, which is this formula that I boxed at in the definition box. Well, so in cylindrical coordinates right here, what's x squared plus y squared together? R squared, all right? This is r squared, all right? Which is actually this one right here, right? I mean, I could have just gone straight to this one, but I mean, it's good to see where is this really coming from. So this will be, well, rho squared equals r squared plus c squared, and this is the square root of r squared plus z squared. Well, we know what r is in this case. What's that? 4 squared plus c squared, which is also 4, and that's the square root. Is that a 16 plus 16? Is that a 32? Square root of 32. All right. And you might want to simplify the square root of 32, which is 16 times 2. Factor out the square root of 16. That's 4 root of 2. All right. So we got rho. Let's see. Let's start filling in the blanks. So rho, which is 4 root of 2, comma, we're missing 2 more. Okay, to find the angle phi. All right, we have a formula to get the angle phi. And actually, well, I didn't mention that was the formula to get the angle. But we got it within the derivation of the other 3 formulas. You know, like in this case, this z equals to rho cosine phi. If we rearrange this cosine phi, that's z over rho. But what's rho in this case? Isn't it the square root of x squared plus y squared plus z squared, which is all this madness here? All right, see how all these formulas are related one way or another? All right, well, and again, in this case, I'm going to use this formula to get phi, and that's arc cos of number 1. Let me do z over the square root of x squared plus y squared plus z squared. But again, what's x squared plus y squared given cylindrical coordinates? Isn't it r squared again? That's arc cos z over the square root of r squared plus z squared. All right, and well, r squared, we know what r is. We know what z is in this case. So that's theta, that's arc cos. That's arc cos of z, which is 4 over this quantity that we actually calculated before, isn't it? 4 root of 2. Cancel the 4's. Theta equals arc cos.
So that means 5.
Which one?
So instead of theta?
Oh yeah, it's 5. Thank you. Phi, or phi rather. That's 1 over root of 2. But that's one of the perfect angles, right? Of the representative angles. What's this one? Isn't it pi over 4? All right. Again, okay. Question to check with information that we know from before. So, do you guys recall how that phi is defined between 0 and pi, right? That's because what's the range of the arc cosine function? Isn't it 0 to pi? So see how these two things are connected actually. So there's actually a big reason. Again, let me pause the video. Okay. What else are we missing? We're missing the angle theta. What's the angle theta? I remember. Actually, it's given, isn't it? Oh, yeah. Let's see. So this is pi over 4. And what's theta? We don't have to calculate anything, right? Because we got it here, right? Pi over 3. And that's it. So that's the equivalent in cylindrical coordinates. All right. Let's do another example. For the next example, I had a little typo at that point. After the 0 should have been a comma right here. Okay, that's a comma.
Another question. I missed, where did the pi over 3 come from? I missed 3.
Oh, in the point, because this is in cylindrical coordinates, this is r theta z, so theta is pi over 3. So just basically just move it to the third component. All right. Now we're going to convert from rectangular and then, from rectangular to spherical and then to cylindrical coordinates. So we're going to do two conversions in the same one. So we have the point 0, -5, and 4. So let's plot that point. Well, actually, I'm going to do the projection into D, because that's going to give us a lot of information, because since this is the spherical system, which in 2D is the circular system, well, this is going to tell us a lot of information right here. All right. Well, number one, in the same way that we had to find r in polar by using the Pythagorean theorem, the square root of the x squared plus y squared, we're going to do something similar to find the rho, but in this case it's basically the Pythagorean theorem or the distance formula in 3 dimensions, which is, okay, let's get the rho. Rho equals to square root of x squared plus y squared plus z squared, and rho equals to the square root of the components 0 squared plus -5 squared plus 4 squared. All right, and that reduces to the square root of 41. Yes, this is not going to be a nice number. In fact, we're going to leave it indicated and not to, in its exact form, not to decimals. All right. So that's rho. Let's find phi. Phi, which is arc cos of z over rho. All right. And well, we know the value of z in this case, which is 4. And that's a 4 over rho, which is the value that we just found, root of 41. And yes, no, this is not going to give us a nice angle like the 1 over the square root of 2 in the previous example. We're going to leave it like this. So what do we have? Phi, rho, and we're missing one piece of information, theta, right? Okay, to get theta.
Question.
Let's have a look. Yes.
Rectangular is just the standard like x and
X, Y, Z. Yes, that is, or Cartesian. That's the other name, right? Or yeah, rectangular Cartesian. All right. Let's focus only on X and Y. What is this going to give us in 2 dimensions? Well, the point 0, -5. All right. And well, from here we can figure out the angle theta. What is that angle? 3 pi over 2. So we can go ahead and write 0, -5, 4, which is really x, y, and z as rho, which is root of 41, and phi, which is arc. Let's leave it like this: arc cos of 4 over root of 41, comma 3 pi over 2. So that's part A in cylindrical coordinates. So now we're going to do the same. Well, we're going to use the information that we have to convert this to cylindrical coordinates. But I think we already have almost everything pretty much, right? We have the angle theta. We have the z, which is given. It's the same one, is 4. So all we need is to find the value of r. All right. So okay, let me label this as in spherical. In spherical and in cylindrical. In cylindrical, it will be okay. So we're going to go from x, y, z to r theta z. Okay, but in this case, 0, -5, 4. Okay, we need to find r. And theta is 3 pi over 2. And what's the value of z? Isn't it the same? But what's r? I mean, to find r, we would have to use the polar version, that is the square root of x squared plus y squared. But in this case, I don't think we need to use the formula to calculate, because how many units are there from the origin to this point? 5 units. So we're done. All right. In some cases, no need to show that calculation. And that calculation, however, if you got a point somewhere over here, well, in that case, use x equals to. So r equals the square root of x squared plus y squared, where x equals to 0 and y equals to, 0 squared plus negative 5 squared. R equals to, well, that's essentially the square root of 25, which is 5 units, which is the same that we got by just observing the picture, right? Which is a valid move. Okay. However,